But I've had a request. I'm gonna put this up on the screen real quick. So I don't know that person's requested this is here, but it has been requested. So maybe they can watch the video later if they're not watching now. Wanted to know if we were going to have. There was a test question we had where you're supposed to find f of x and g of x so that f of g of x equaled like 9 over x squared plus 7. And you got to create the f and g of x to make that work. There's multiple ways to do that, but whatever happens, you got to make g of x where you substitute it in, and when you substitute it into f of x, it's going to end up looking like that. So it could be that f of x is as simple as x plus 7. And then you substitute in 9 over x squared. So when you substitute 9 over x squared in for x, it's going to look like that. Or you could have said that f of x was 9 over x plus 7. And then g of x was just x squared. So when you substitute x squared into x, it would still look like that. Again, there's multiple ways to do that. You just have to create two equations where when you substitute g of x into f of x, it's going to end up looking like that. Like I said, there are multiple ways to do that. You might even get creative and come up with some more. But just showing that real quick. All right, let's see. What do we have going on this week? This week we have, let me go back here and look at Algebra 3. We finished up last week with lessons 1 and 2, and that was dealing with long division of polynomials. Yay, fun, right? No, not fun, but something that's a skill that we need to know how to do. Then we looked at synthetic division, which was a nice shortcut as opposed to long division. But remember, it only worked in certain circumstances. First of all, you had to be dividing by like an x plus or minus something. We couldn't do it with an x squared or x to the third. We couldn't divide that in using synthetic division. We can do it with long division. That would work. But we cannot do that with synthetic. Synthetic is a nice shortcut when you just have an x binomial term. So what I want to look at today is lessons 3 and 4, because that's what we have this week. Let me just remind everyone this week, this is a great week to get caught up. If you are behind, and some of you are a little bit behind, I'm looking at this, most everyone, with just a few exceptions, are up to 3.02, which is what we should have turned in yesterday, 3.01, 3.02. There's a few people that are still behind some lessons and have not got everything turned in up to that point. So if you're behind, this is a good week for you because there will be no classes past tomorrow. We have classes today, we have classes tomorrow, and then there will be no meets the rest of the week at all. So no mandatory meets, no optional meets, no meets period, Wednesday through Friday this week. This is parent-teacher conferences tomorrow night after school from 4 to 8. We will be up here at BHS, where the virtual school is located at. So tomorrow night from 4 to 8, we'll be here. And then Wednesday, Thursday, Friday, we'll be in teachers' meetings on Wednesdays and Thursday. We will not be on any meets. So you only have classes today and tomorrow. And then the rest of the week, you're on your own. So, you can always email a teacher, but we're going to be in meetings. We're not going to have a chance to email you back until Friday, probably at the earliest. So if you're behind, this is a great opportunity for you. If you're current and get everything done Monday and Tuesday, you'll just have 5 days off, right? Wednesday through Sunday, because there will not be anything else happening here at the school for that winter break for you guys. Not a break for us. We're in meetings and doing stuff. So good chance to get caught up. All right, let's look at the lessons for this week, 3.03. Oh, I do want to mention one more thing before we get into this week's lesson. In Module 3, I've added an assessment towards the end. I've skipped this in the first couple of units, but it's getting to where we're getting into the good stuff, and I want to make sure you understand. When we get just before the test at the end of this module, when we get the first week in November, there is a 3.10 discussion-based assessment. Assessment, that means it's a test. It's a quiz, it's a test. So it is an evidence of learning grade. But that is, there's nothing in Buzz on that. There's just an assignment, but it doesn't have any questions or details or anything. Because that is an opportunity where you and I get together, and I'll probably do some of that in class on that week, where we'll just do breakout rooms, and it'll just be one student at a time in the breakout room, or we'll do it during flex or find other times. But basically, I ask you questions about this module. Hey, how do you use Descartes' rule of signs to determine how many rational roots a polynomial has or something? I'll just be asking you all the different things that we learned from this module. And if you can explain this to me, then you'll get a nice grade for that. And I know you're ready for the test. If you can't explain these things to me, then you're not ready for the test. All right. So this is going to be a discussion-based assessment where I'm asking you questions and ask you how to do things, and you need to be able to explain them to me. So when you're going through these lessons, make sure you're trying those practice problems in the lessons, not the assignment afterwards, not the homework practice stuff afterwards. In the lesson, when it says try this, and then it has check your answer, make sure you know how to do those. That way, if you can do those, when I'm asking you questions, you'll understand how to do all of that. You won't have any problems. If you're skipping those lessons, if you're skipping those practice problems in the lessons, then you may struggle and not have a good grade on that discussion-based assessment. So make sure you're learning this stuff. If you're not understanding things as you're going through the lessons, make sure you're getting with me and getting better understanding before we get to that discussion-based assessment at the end of the unit. So, all right, let's look at 3.03 and 3.04 this morning. I'm going to put my camera back up here. And let's talk about what is in lesson 3.03. 3.03 talks about a couple of theorems. We have a few theorems that we're learning in this unit. And we're going to start with the fundamental theorem of algebra. The fundamental theorem of algebra. I'm going to say fundamental. Let me go and spell it out here. Fundamental theorem of algebra. All right, fundamental theorem of algebra. And here is what the fundamental theorem of algebra talks about. Well, I'm gonna start this out. I'm actually going to put a question up here. I want you guys to respond in the chat. If I have this equation right here, okay, x squared minus 3x minus 28. How many zeros will that have? How many solutions for x will that have? That would make that equal to 0. Put that in the chat. I'll have the chat open. How many zeros would we expect this equation to have? See who's awake this morning. You can put a guess. If you don't know, put a guess. By the fundamental theorem of algebra, how many zeros would we expect this to be? How many solutions? If we set that equal to 0, how many answers would we expect there to be? Zeros of that equation. Oh, someone said 2. Anyone else agree or have a different answer? 2? 2? Well, 2 seems to be the popular answer here. All right, let's talk about that. The fundamental theorem of algebra says this: since this is x squared, that is the largest term. The largest term is squared. We expect there to be 2 zeros. 2 zeros. Now, before we started getting into Algebra 3, we talked about how there could be 2 or 1 or 0 solutions to this, right? Because when you graph a quadratic equation, if it looks like this, then we know there's two zeros, right? There's one right there and there's one right there. But if we graph it and it looks like this, then there's only one zero. It only touches in one place. And of course, if it's higher like this, we said there are no zeros because it never touches the x-axis. But we're in algebra 3 now. And in algebra 3, we understand that in a situation like this, it will have two imaginary zeros. Right? We talked about where it might be like 8 plus 2i. Maybe that's one of the zeros, 8 plus 2i, with I being an imaginary number, right? And then in the last module, we learned that if this is one of the zeros, then we automatically know that this is a zero because they come in pairs. When you have one complex zero, this is called a complex zero, imaginary zero. Put the word complex up there also. So it's really complex zeros that they come in pairs. There's always two of them, and they will have one as a positive and one as a negative. 8 plus 2i and 8 minus 2a. This is the conjugate for that one. Conjugate. So they come in conjugate pairs. So in this case, there are two imaginary zeros. So since they come in pairs, we know that to be the case. So the fundamental theorem of algebra says whatever the highest power is, there are that many zeros, guaranteed. There are that many zeros. So if we look at like this one right here, if we wanted to know what the zeros are, because this one does actually have two zeros, when we factor that, we'll find out that the factors are x plus 4 and x minus 7. We'll multiply that together, we get this up here. So if this is the factors, that means the zeros are x equals negative 4 and x equals 7. That's the two zeros. This will be at negative 4. This will be at 7 if we graphed it. Because negative 4 plus 4 is 0, or 7 minus 7 is 0. All right, so we know that this would equal these two zeros. Now, when we were looking in lessons 1 and lesson 2, we talked about division, dividing polynomials. So if we had negative 4x to the third plus 21x squared minus 25, and we said, okay, what if we divide that by x minus 5? If we divide that by x minus 5, we can find out if this is one of the factors. Because if the remainder is 0, if the remainder is 0, that means this divides perfectly into there, and it will be a factor, like these were factors of that problem up above. So we could do that. Since this is an x minus 5, we could do that with synthetic division, right? Because this is just an x. So if it's x minus 5, we divide by 5 with synthetic division. Remember that? And we have to use just the coefficients, starting with x to the third. So the coefficient of x to the third is negative 4. The coefficient of x squared is 21. What's the coefficient of x? We can't skip that. Remember, it's synthetic division. We have to do everything, starting x third, x squared, x. Since there's no x, there's a coefficient of 0. And then we have the negative 25 for the x to the 0 power coefficient. Synthetic division, remember, we drop the first one straight down, negative 4. Then we multiply. 5 times negative 4 is 20. We add those. Oh, that's negative 20. 5 times negative 4 is negative 20. Add that to be 1. 5 times 1 is 5. Add that is 5. 5 times 5 is 25. Negative 25 plus 25 is 0. So this is a factor. So that means if we take this and we factor it, it's going to be x minus 5 times negative 4x squared. We go one less than we started with, plus x plus 5. So those are factors of this right here. Right? Those are factors of this. So we know that 5 is one of the factors. And there should be 2 more. Now we could then take this. It's a quadratic equation. We can use the quadratic formula. And the quadratic formula would tell us we can try to factor that. We can complete the square. We can use grouping, however you want to. And this is where our other 2 answers should be. And we should end up with 3 zeros. Now, using the quadratic formula, you'll have that negative b plus or minus b squared minus 4ac over 2a. That's a quadratic formula. This part right here, the b squared minus 4ac, that will tell you if these answers are real or imaginary. Because if you do the b squared minus 4ac, and let's do that, b is 1. So this would be 1 squared is 1, minus 4 times a, negative 4, times c, which is 5. 1, negative 4 times negative 4 is 16, times 5 is 80, plus 1 is 81. Since this is a positive number, it's going to be 2 real roots. If this was a negative underneath the square root, then we know the answers are imaginary. There'd be 2 imaginary numbers, but it's not. That's a positive 81, which is equals 9, right? So we know that there will actually be 2 real answers because this is negative 1 plus or minus 9 over 2 times a, which means negative 8. So negative 1 plus 9 would be 8 over negative 8. So negative 1 is also a root. And negative 1 minus 9 is negative 10 over negative 8. So that means 5/4 when you simplify that. One of our roots is a fraction. 5/4, 5/4, negative 1, and 5 are the 3 roots of this polynomial we had up here. So we can figure that out. So another way we can tell if something is a root, other than synthetic division. All right, let's use the remainder theorem. There's something called the remainder theorem. This was the factor theorem. The factor theorem, when we divide that in there and we get a remainder of 0, this is a factor theorem. That if the remainder is 0, then this is a factor. That's a factor. Factor theorem tells us that. Let's look at the remainder theorem. Remainder. Let me put that out there. Remainder theorem. Lots of theorems in Algebra 3. We're getting into the bigger math, and these theorems give us shortcuts a lot of time. So let's look at a bigger polynomial. Let's go x to the 4th plus 11x to the 3rd plus 26x squared plus 15x minus 17. Ooh, there's a nice big one. And we want to know, is x plus 8 a factor? Is x plus 8 a factor of that? Well, we could use the factor theorem and take negative 8 and divide it in to that with synthetic division. And if there's a remainder 0, then that would tell us, yes, it is. Or if the remainder is not 0, no, it's not. But we can also use the remainder theorem. And using the remainder theorem, is 2 different ways. One's the synthetic if there's a remainder, but there's also, if this is x plus 8, that means negative 8 is the number we're testing. We're going to substitute that in f of negative 8. So this becomes negative 8 to the 4th power plus 11 times negative 8 to the 3rd power plus 26 times negative 8 squared plus 15 times negative 8 minus 17. Guys, got to get good at this. When you're substituting the number in, all you do is wherever there's an x becomes that number. We do this a lot for the rest of mathematics here. So make sure you're understand how to do that. Just like when we substitute g of x in, we're just taking g of x and putting it everywhere there's an x. Okay, so then we simplify this. Say negative 8 to the 4th power is, I already have this written down, so I don't have all these in my head. A lot of these I do. And then times 11, negative 8 to the 3rd power is negative 512. That's negative 8 times negative 8 times negative 8. Plus 26 to negative 8 squared is 64. 15 times negative 8 is negative 120 minus 17. Okay, so we're just simplifying still. We have 4096. 11 times negative 512 is negative 5,632. 26 times 64 is 1664. And this is minus 137 when I combine those. So if we do all of this number minus this number plus this number minus this number, we end up with -9. This is what the remainder would be if we did synthetic division. That means this is not a factor because there's a remainder. If this was 0, then hey, x plus 8 is a factor. We figured out a factor, but this is not a factor because the remainder is not 0. That's the remainder theorem. If there is a remainder, that is not a factor. So that kind of tells us a few things right there. So the things that we're using here, if we have any function, f of x, and we find out that x minus a is a factor, that means a 0 would be a, right? That's one of the zeros, x minus a. If this is x minus 2, then 2 is one of our zeros. When you graph it, it would cross the x-axis at 2. If we substitute 2 in it, it would equal 0 because 2 would be a 0 if this was x minus 2. That's an a, so it can be for any. All right. So that tells us that. So then we would know for x minus a, we could find that out by long division, right? If we're trying to figure out if that's a 0, we can do long division, x minus a into that function, and that'll tell us. We can do synthetic division. Synthetic division, if there's a remainder of 0, that tells us that. Or we can factor the original polynomial. Either grouping, completing the square, grouping. However, if it's a quadratic, we can use the quadratic formula, depending on what the original function is. So that would tell us a lot about x minus a being a factor. Then if that is a factor, and we know that a is one of the zeros, then that tells us that the graph of f of x crosses x-axis at a comma 0. Right? So if we know that this is one of the zeros, then we know that when we graph it, it's going to cross the axis there. We also know we can substitute. A into x minus a, and that will equal 0. Right? So if it's 2, then 2 minus 2 would be that 0. And we also know that if we substitute, I'm going to do that, substitute a into f of x, it will equal 0 because it's a 0. So if we substitute an f of x, it's going to be 0. If we substitute into that factor, it'll equal 0. Tells us a lot about our polynomial and our factors when we do that. So that is a lot of lesson 3. Goes over these remainder theorem, the factor theorem, and the fundamental theorem of algebra. That's lesson 3. There are videos in there. There's lessons that take some time to go through that. Do those problems that it's testing you on and make sure you understand how to do that. Now, lesson 4, we're going to get into the rational root theorem. And this is some shortcuts, because some of these problems we're getting into now can take a lot of time and a lot of paper. Rational root theorem. And then we're also going to get into Descartes. He was a French mathematician, lived about 400 years ago, in the 1700s. Descartes' rule of signs. Descartes' rule of signs. This is what lesson 4 is about. The rational root theorem, Descartes' rule of signs. So here's how it works. If we have f of x equals 3x to the third plus x squared plus 21x minus 11. Okay, the rational root theorem can help us figure out what the roots might be, what the rational roots might be, not the complex roots. All right, if there's imaginary roots, this does not help us find imaginary roots, but it does help us figure out what the rational roots are, the real roots that we could graph and find. this will help us narrow it down. And here's how it does that. We look at the coefficient of the first term, the largest term when it's in correct order, and we look at the constant on the end, right? So we're going to call this one P. We'll call this one Q. So our P's and Q's. All right. Oh, wait a minute. I'll put those backwards. Our P is our constant. P and Q. And then when we look at P over Q, that will tell us all of the possible rational roots this has. So let me ask you another chat opportunity for those of you still awake. Negative 11. What are the roots of negative 11? What numbers can I multiply together to get negative 11? Give me all of the roots that we can do that. I'll wait. Negative 11. What numbers can we multiply together to get negative 11? All the possibilities. Starting easy. This is like elementary school math. Negative 1 and what? That's one of the roots. We can multiply negative 1 times 11. So yeah, so we could multiply negative 1 times 11, or we can multiply a positive 1 times negative 11, and that's about it. That's it. That's all the roots. So we can just simplify it to say plus or minus 1, plus or minus 11. That's the only options there are to get negative 11, right? If the 1 is positive, then this is negative. If the 1's negative, that's positive. So plus or minus 1, plus or minus 11. Then we do the same thing with this. 3 is the same thing. Plus or minus 1, plus or minus 3. That's it. We don't have that many options. So to figure out what the possible rational roots are, we take P and put it over Q, every combination. So let's look at the 1. If the 1 is over 1, that's just a plus or minus 1. 1 divided by 1. 1 divided by 3 means it could be a plus or minus 1/3. They're all plus or minus because it could be either way to get that. Plus or minus 1, plus or minus 1/3. Okay, that's all the possibilities of the 1. Now the 11. 11 over 1 is just plus or minus 11. 11 over 3, plus or minus 11/3. We can't simplify that. That's just it. So these are the only possibilities. If this was graphed and it has some real rational roots, it's going to cross the x-axis at either plus 1 or minus 1, or plus 1/3 or minus 1/3, or plus 11 or minus 11, plus 11/3 or minus 11/3. That's the only possibilities. That's what the rational root theorem tells us. It has to be one of those 8, either the positive or the negative. All right, and how can we find those? Well, we could start just using synthetic division. We could do that. We could test it 8 times, right? We can say, okay, I'll multiply 1, and then I'll multiply negative 1, and I'll do each of those with synthetic division. And I can narrow it down to those 8 and figure out what the rational real roots are. But you're thinking, okay, that's still a lot of work. I'm having to take 8 numbers. And what if there's more than 8? Sometimes there is. Sometimes there's 10 or 14 or a whole bunch of possibilities. We got lucky. These are both prime numbers. So there's not that many options. Well, we can narrow it down even further with Descartes' rule of signs. And so his rule of signs says, look at your equation and see how many times does the sign change. Okay, this is a positive number, right? This is a positive number. The sign did not change. This is a positive number. The sign did not change. This is a negative number. Oh, we have one sign change, 1. So what Descartes' rule of sign tells us is that there is one positive real root. 1, because the sign changed 1 time. Oh, so if we were doing synthetic division and we checked in 1, that didn't work. 1/3 worked. Hey, what if 1/3 worked? We wouldn't have to test 11 and 11/3 because we know there's only one possible real root. That's it. There's not more than one. That's what Descartes' rule of signs tells us. But it can also tell us how many possible negative roots there are. So we don't have to check -1, -1/3, -11, -11/3 if we can figure out how many possible there are. And the way Descartes says to check that is we take -x and we substitute it in. So that would be 3 times -x to the third power plus -x squared plus 21 times -x, and then -11 is just -11. So simplify this. -x to the third power. -x times -x times -x. -x times negative makes it positive, but then it becomes negative again. So this is going to be negative. So that's -3x to the third power, right? Because that's a negative. -x squared becomes positive again. So this is still just positive x squared. A positive 21 times a negative x is a negative 21x. And then we still have the -11. So how many sign changes are there when we use -x? Oop, sign changed right there. There's one. Went from negative to positive. Went from positive back to a negative. Positive, negative. There's one. Negative to a negative. Okay, it did not change. So there are possibly two. Oh, not positive. Negative real rational roots. 2. Now here's the key. The other roots there could be is complex roots, which means they are imaginary roots, which means when you graph that, you will not see these because it will not cross the x-axis at an imaginary root. But we know 3x to the third has 3 roots, but we don't know how many of them are imaginary. Now we know one is positive because of what came up with. Could be 2 negative, but it could be that they're not negative. They could be imaginary instead. Because remember, with imaginary roots, if one of the roots is 2 plus 3i, if that turns out to be one of the roots of this and it's imaginary, then it has to be 2 minus 3i. There's no choice. They always come in pairs. Pairs. There's always pairs of these. So you always have to consider that these might be imaginary. So this means there's either 0 or 2 imaginary or negative roots. And there could be 0 or 2 complex roots. Now there's definitely one here because we can't take a pair away from that because there's not going to be -1. If there's 1, it's 1. But if it's 2, it could be 2 or 0. If it was 5, it could be 5, it could be 3, it could be 1 because there would be pairs of complex numbers. It'd be 0 or 2 or 4 of the imaginary roots because they always come in pairs. So anytime you have it, tell you how many roots it has. You have to also consider negative pairs of roots less than that. So let me look at one more possibility here. If we had f of x and it equaled -7x to the 5th minus 10x to the 4th plus 3x to the 3rd plus 4x squared minus 13x plus 9. We want to know how many positive real roots, how many negative, and how many complex or imaginary roots could be. Positive real roots, negative real roots, or complex imaginary roots. So let's use Descartes' rule of signs. Negative to a negative did not change. Negative to a positive, that one changed signs. Positive to a positive did not change. Positive to a negative, that one changed signs. Negative to a positive, that changed signs. So there's 1, there's 2, 3 possibilities. So there might be 3 possible positive roots, or there's only 1. There's either 3 or there's 1. There can't be more than 3. So if you're testing numbers, there can't be more than 3. And we can figure out which numbers to test, right? Because the roots of 9 are 1, 3, 9, all positive or negative. That's all numbers we can multiply together to get 9. 7 is plus or minus 1, plus or minus 7. So the possible roots are 1 over 1, 1 over 7, plus or minus 1/7, 3 over 1, 3 over 7, plus or minus 3/7, plus or minus 9, and plus or minus 9/7. So there's 12 possible roots. But once you find 3 of them, you know there can't be any more. How about negative roots? Let's substitute a negative x in here. F of negative x equals negative 7 times negative x to the 5th minus 10 times negative x to the 4th plus 3 times negative x to the 3rd plus 4 times negative x squared minus 13 times negative x plus 9. So a negative x to the 5th power is going to be a negative x to the 5th. Negative times a negative, so this is going to be 7x to the 5th. It's going to become positive because that's going to be a negative. That's going to be a negative. Negative x to the 4th ends up positive x to the 4th. So this will stay negative 10 x to the 4th. Negative x to the 3rd is a negative times a positive, so that becomes a negative 3x to the 3rd. Negative x squared is positive x squared because negative x times negative x is a positive x. So that becomes plus 4x squared. Negative 13 times negative x is a positive 13x and positive 9. So how many sign changes did we get? 1. And then that stays the same. 1. That's it. We have 1, 2 sign changes. So possible negative roots, there could be 2 or could be 0. We know there are 5 total. Right. So if there's 3 positive and 2 negative, then there are 0 complex roots. But if there's 1 positive and 2 negative, then there could be 2. Or it could be there's only 1 positive and 0 negative, and it means 4. So this is all the possibilities. 3 or 1, 2 or 0. So if you're testing the negative ones with synthetic division and you find 2 negative ones, you're done. If you check the first 5 negative ones and none of them work with synthetic division, there's no need to check the last one because 1 negative root is not a possibility. So if you only have 1 left and none of them have worked, it's not going to be that last one either. So this gives you some shortcuts in finding possible roots of this great big polynomial that we have a hard time factoring. So we have to start dividing in roots with synthetic division and trying to figure out what are the roots of that. What are the complex roots of that, which we can find when we get down to quadratic equations. A lot of time we can find that with the quadratic formula. So a lot that we've looked at there, a lot that we've looked at. Let's see, I'm going to stop presenting that. Okay, so what did we look at today? We have looked at the fundamental theorem of algebra. We've looked at the factor theorem. We've looked at the remainder theorem. We've looked at the rational root theorem, and we looked at Descartes' rule of signs. So, and these guys figured this out 400 years ago, these shortcuts, and that's what we're able to use today because they have figured those out, proven those, and they work. So if you are confused, go through the lessons. Make sure you go through the lessons anyway. There are videos in there that give more explanation on this. There's lots of examples in there. Have your pencil and paper when you go through these lessons. When it puts up a problem there and it says check your answer, work it first, then check your answer and see if you're understanding how to do that. Because if you're not getting the same answer in the lesson, then you're missing something. And then the lesson will show you step by step where you can say, oh, that's what I did wrong right there. Right. So if you can do that and do those lesson problems, then the practice homework assignment afterwards ought to be a lot easier because you already know that you're doing it correctly. And here's the great thing. Save all those notes, those problems you work and you get it right. And you take those notes because when the test comes around, Woo, what am I doing? I'm pulling out all my notes and I'm looking at the test and I say, oh, I worked a problem like that. And I'm going to flip through and I'm going to find it and say, oh, there it is. There's what I did. All right. So let's see that problem. All right. And I'll work that, but I know how to work it because I had a similar problem that I've already done in my notes. So that's what's great about taking notes and doing the practice problems is that you can pull them out on the test knowing that you've already done something like that. And all you have to do is apply that same process to a new problem. All right. Okay, with that, I will let you go. Go enjoy the rest of your day. We no class on Wednesday, no class on Friday, right? It's a break this week. There's a good chance to get caught up if you need to. Hang around if you have questions. Have a great break.
Let's get out of here. Word to your multiples.
Math, baby. We're learning math, baby.